Good morning. Today we will start a new topic on chemical propellants. Let us first be clear what we mean by a propellant. We told ourselves any substance which is used for propulsion of a rocket is known as a propellant. It could be anything, it could be something like a gas, the gas could be cold at high pressure, the gas could be hot, therefore it is a propellant. Maybe we even considered these boys throwing stones and stones were the propellant. It could be anything, it could be a charged particle, it could be a plasma, it could be anything. But what we consider in the next 3 classes is what constitutes chemical propellants, and then we go to chemical rockets, and chemical rockets are solid propellant rockets, liquid propellant rockets, hybrid rockets and so on. Therefore, let us see what are the requirements. Before we study anything, we must know what are the requirements, what is the requirement of a propellant. I think that is the basic with which we should get started, and we have studied in nozzles that when we look at any rocket chamber, let us say this is a chamber, you have a nozzle which is coming, our aim is to get as high a jet velocity as possible, and to get a high jet velocity we told ourselves in the chamber I would require a high value of the chamber pressure and a high value of the chamber temperature. We also told ourselves we require a small molecular mass of the gases which are being expended out, in which case I will get a higher jet velocity. And what was the term we used to determine all this? We used the term C star, which is a transfer function between what is generated or what is sent into the combustion chamber and the high pressure, high temperature, low molecular mass combustion gases which are generated. And what was the expression for C star? We had the expression under root R into temperature of the hot gases divided by the capital gamma, and this was a specific gas constant which in terms of the universal gas constant we could write it as R naught Tc by the molecular mass of the gases which are sent out through the nozzle, and this is again under root into we have 1 over gamma which is a function of gamma. Therefore, this should tell us what we really require in a propellant to do. What we require is this transfer function which tells the capacity of this particular chamber to generate high pressure gases must be high, or rather this characteristic velocity which was a transfer function of the propellant, of the chemical propellant, any propellant, say chemical propellant, must be large, right. If it has to be large, obviously we have to tell ourselves, well, C star is equal to under root Tc, rather Tc must be large 0.1, or the molecular mass of the gases which are escaping through the nozzle must be small, okay. Anything else? See, if we have the combination of gamma, we told gamma must be small because capital gamma was equal to under root gamma 2 over gamma plus 1 to the power gamma plus 1 divided by 2 gamma minus 1. The requirement was also that gamma should be small, it is not as sensitive as Tc and m were. Therefore, basically we are looking at the following, maybe I would require Tc to be large, the molecular mass of the gases to be small, maybe the specific heat ratio also to be a small number. If I can have propellants which could generate gases such that the temperature of the hot gases, the pressure of the gases should be large, the molecular mass of the gases must be small, and the specific heat ratio of the gases must be small. This is what a propellant should do. How do you get it? Let us take a look at Tc. What will give me a high value of Tc? If I have a chemical propellant, and now we must say I am talking of chemicals, there are a large number of chemicals available, I cannot use all these chemicals. And why do we use a chemical? Maybe I want the chemicals to react with each other or react and generate hot gases. Why hot gases? If I have hot gas, I could have Tc which could be a higher number. Therefore, basically I am looking at chemicals, because I am looking at chemical propellants, substances which are chemicals which could react, generate hot gases, and these hot gases could be at a high temperature. To generate a high temperature gases, the heat release in the chemical reaction should be large, and therefore if heat release is large divided by, that is heat release per unit mass is large, per unit mass of propellant is large, divided by, let us say, the specific heat of the gases. Maybe I am burning at constant pressure, therefore the specific heat at constant pressure is small. I can have, let us say, a large value of Tc. I have introduced one more word. All what I am saying is I have chemicals, these chemicals react, generate hot gases at high temperature. When do I get high temperature? If the heat release per unit mass is a large number, and if I take Cp, because Cp into delta T is the heat release, if I have a small value of the specific heat ratio, then I can get a high value of temperature. Therefore, what do I say? Now I put another number here. Maybe I say the specific heat of the gases, let us say specific heat at constant pressure, must be also a small number. Well, these are the requirements I am looking at. Well, in terms of this, maybe Q must also be large, the heat release must be a large number. Therefore, these are the basic requirements of a chemical, and therefore I am looking at what are the requirements of the chemicals which can do the job. Well, the chemicals should have a large value of heat release, a small value of specific heat release, maybe a small molecular mass of the product gases which are generated, a high value of the temperature, and perhaps a small value of gamma. If we can address all these points together, maybe I could have a chemical or a few chemicals out of the maybe millions of chemicals which are available. I can zero in on 4 or 5 which can be used as chemical rocket propellants or rocket propellants, which are maybe chemicals or chemical rocket propellants, let us say, and this is what I am going to do in this class. Therefore, let us ask ourselves, well, to determine temperature I need heat release and also specific heat. Let me start with something simple. Under what conditions will I get a low molecular mass of the gases which are generated? Let us say I have a chemical, and the chemical by reaction generates hot gases or gases. Therefore, basically I must take a look at the atomic mass or the mass of the elements, atomic mass of elements in the chemical propellant must be small. Why should it be small? If the atomic mass is small, the product gases will also have low atomic mass. Therefore, let us take a look. In chemistry we have what is known as a periodic table, and what does periodic table do? It arranges all the elements in terms of its atomic number, and this is what we will first take a look at it. Let us say this is the periodic table over here given. You have elements starting with an atomic number of 1, the atomic mass of hydrogen whose atomic number is 1, the next is helium, atomic number is 2, the atomic mass is 4, next is lithium, number 3, the mass of lithium atom is 6.9, beryllium 4, atomic mass is 9, boron 5, the atomic mass is 10, and so on, carbon 6, 12, and so on. We go to nitrogen, oxygen, fluorine. Then I have neon, neon is used for lighting, it is an inert gas. Then I have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, and chlorine. I stop at 17 because already the atomic number has increased to 17, and as you see the atomic mass has increased from 1 to almost 36. The values of the atomic mass which I have shown here are with respect to hydrogen. Beyond this, if I go, the atomic mass is so large that any product which is formed will become very heavy. What does this table tell us? Let us take a particular case, maybe hydrogen has a low atomic mass, and therefore even if I take a hydrogen molecule H2 whose molecular mass is 2, Well, it is lower than anything else, therefore, it is a very viable propellant from the molecular mass point of view. I next go to helium. Helium is inert. Well, it can be used as a cold gas, cannot be used as a chemical propellant, I will not consider it. Well, lithium is used in solid propellants because of its low atomic mass, we will have to take a look at it when we study solid propellants. Well, beryllium, boron are used, the masses are still small at atomic mass of 9 and 10. Carbon is a part of any hydrocarbon, carbon and hydrogen together, well, we cannot escape. Fortunately for us, carbon has an atomic mass of 12, which is still not very bad. Nitrogen is inert, but most of the substances in nature are associated with nitrogen. We find that the atomic mass of nitrogen is 14. Oxygen is a powerful oxidizer, maybe it is used for oxidizing any fuel, it has its atomic mass is 16, molecular mass is 32. Fluorine is a very reactive oxidizer, much more reactive than oxygen, very near to oxygen itself, its atomic mass is 19. Well, neon is inert, I cannot consider it. Sodium is very reactive metal, I drop sodium in water, it just explodes, I cannot use it. Magnesium, you would have seen magnesium ribbon being used as a for Diwali function, you light it and it glows, it is a reactive metal, very reactive, therefore it is going to be difficult to use magnesium as it is. Well, aluminum is a light metal, atomic mass is 27, therefore this tells us, supposing I have to use a metal, better I use aluminum rather than iron, which is going to be much heavier. Only aluminum is used compared to iron, iron is never used. Silicon is something which is a light material, but it is not reactive, I will not consider. Phosphorus is very reactive, I cannot consider. Sulfur has a molecular atomic mass of 32, chlorine is again an oxidizer with atomic mass of 35. Beyond this, you go to argon and other elements, and they become progressively more and more heavier and they cannot be used. Therefore, all what we say is, out of all the chemicals, I can now isolate something like up to Cl, which has an atomic number of 17, which are little favorable from the molecular mass point of view. From molecular mass point of view, we know, yes, better to select some of the lighter elements. I show this again in the next slide, wherein I now choose myself on hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, aluminum, sulfur and chlorine, and I say, well, these are the elements which I use in my chemicals, it will be better for me to get a low value of molecular mass, and hence it is more desirable. Therefore, we address the first point, namely the molecular mass point of view. When will my molecular mass of my products be small? When the atomic mass of the elements of what I consider should be small, and therefore I localize myself into something saying, well, these are the things which I should be using. Well, fluorine is very reactive, it is more reactive than oxygen, and in fact liquid fluorine they did try to use for rockets, it used to just corrode the tanks itself, and therefore it was used in one of the Delta missions, but subsequently I do not find it being used. But anyway, we will keep it here, we will see under what conditions fluorine can be used. Well, oxygen, fluorine, chlorine are oxidizers, maybe hydrogen is a fuel, lithium, beryllium, boron, carbon and aluminum are fuels. Aluminum is a metal which can burn. Something which is interesting, see during Diwali function you all would have seen this sparkler. What is a sparkler? It consists of a composition which is known as a black powder composition, and it is coated on a rod, maybe a steel rod or something. You could have it either as a composition, or you could have it the same sparkler, you could also have some metals which are embedded in the sparkler. When the sparkler burns, the metal gives violent energy, right, because the metal is so strong, that means it is so dense that it can produce much more energy. Therefore, metals such as aluminum, maybe boron, maybe beryllium can also be used as fuel. Therefore, now we tell ourselves, well, I have looked at one step of it, maybe from molecular mass point of view, Let me take a look at the next step, maybe from the temperature point of view, whether I should have some of these elements, or what should be the composition of gases such that I get a high value of temperature. Maybe if you go through this, maybe half of our work in choosing a propellant will be over. Let me come to the second part therefore. Let us take a look at the specific heat. Of maybe the products of burning or products of a chemical reaction which are escaping through the nozzle. We tell ourselves, well, Tc goes as heat release divided by the specific heat. I would like to have Cp as small as possible. Well, this is thermal, all of us know it. All of us know that a single atom like hydrogen or oxygen atom or oxygen atom that is monoatomic has a specific heat of the order of something like 20 joule per mole Kelvin, unit of specific heat, per mole per Kelvin. My unit of measure is mole, joule per mole Kelvin. If I have diatomic molecules like O2, hydrogen or OH, that is two of them together, it increases to something like 35 joule per mole Kelvin. If I have still more complicated things like CO2, 3 of them together, well, it increases to almost like 62 or 63, let us say 65 joule per mole Kelvin. Why should specific heat increase as the molecule changes from monoatomic to diatomic to triatomic and all that? Why should it go? What will be your reaction? Why should it increase? Mind you, the unit is per mole Kelvin. Why should it go up? Yeah. What happens? Let us take a simple molecule like let us say oxygen atom. It is just O. If I take O2, well, it is O2 over here, or let us say we are not bothered about double bond, single bond, it is all bonded together, let us say like this. Now, when I heat this, the degrees of freedom are smaller, it absorbs less amount of energy. This will absorb little more energy because I have more degrees of freedom, it is more complex, it absorbs. If I have CO like this CO2, it can still have more bonds, more energy it can absorb, and therefore the energy absorbed per mole of a monoatomic substance is less, diatomic is more, triatomic is more, and so on, it increases. Therefore, let us see some values of them. We say, well, monatomic has the lowest, diatomic has higher value, triatomic has still higher value, and as I go on, the molecular, the specific heat keeps increasing. Therefore, from this point of view, I should say if my product gases are all monatomic, well, I am better off. If it is diatomic, well, I can tolerate it, it is still high, and so on. That means the products of combustion must be, what do we say, must be simple, not complex. In which case I can have a small value of Cp. I put down some of the values of Cp in the next slide over here. This here I say helium, which is monoatomic, at two temperatures of 2000 Kelvin and 3000 Kelvin, with change in temperature there is hardly any change. Therefore, irrespective of temperature, for the monoatomic, maybe helium, hydrogen atom, oxygen atom, the value is around 20. If I go to diatomic gases, hydrogen, OH, maybe HCl, maybe N2, maybe CO, NO, see, all have a ballpark number of around 35, and the change in temperature is not that profound. Therefore, I say I have an average value here. When I say a triatomic gas, well, it is even higher, it is of the order of 60 to 60, 51 to something like 60 here, water is around 51 to 58, this CO2 is between 60 and 63, maybe around 63, 64 is what is the average value. Therefore, I find monatomic has around 20, this is around 35 to 36, this is around 60 to 65. Therefore, this is the range. Therefore, I would still like to get, according to this specific heat point of view, if my product gases were all dissociated in hydrogen and oxygen atoms, or diatomic, it is better. If I keep on increasing the complexity, my specific heat keeps increasing, and I will not be able to get a high temperature, and therefore, I say specific heat must be small. Okay? Therefore, we have looked at two criterion, namely we looked at the criterion of molecular mass. For that we say, well, the atomic mass must be small or atomic number must be low. Second, we say Cp means the product of gases which come out of the chemical reactions of the chemicals must be somewhat simple or dissociated. Okay? Let us go to the next one. Before I come back to the temperature and heat release, let us take a look at gamma. We said gamma should also be small. What does this imply? Gamma has to be small. If we go through thermodynamics and the kinetic theory of gases, we say gamma we defined as equal to Cp by Cv, which in terms of the degrees of freedom of the molecule can be written as 1 plus 2 over something like n plus 3, where n shows the degrees of freedom of the gas over and above the translational modes. Let me qualify. Supposing I have an oxygen atom, this being just an atom, it can either move in this direction, or in this direction. That means it has 3 degrees of freedom. If I have an oxygen molecule, well, it is in addition to translation in the 3 directions, it could also vibrate, it could also rotate. Therefore, it has a degree of freedom of 2 compared to the atom which only translates. I could also have atoms in which we could have maybe C3H8, which becomes more complicated. It could have lot of freedom compared to a simple translation, and for instance, if I take CCl4 carbon tetrachloride, the degrees of freedom of this are almost something like 13 or 14, because it has so much, the molecule becomes more complex, it has more degrees of freedom. Therefore, for gamma value for a monoatomic gas for which the number of degrees of freedom are only 3 and n shows more than 3, that means we say for monoatomic gases, like let us say gamma for helium is equal to 1 plus 2 by 3, which is equal to 1.67. For diatomic gases like oxygen, hydrogen, nitrogen and all that, you have 1 plus 2 by 5, which is 1.4. Maybe as it becomes very complex, like gamma for CCl4 carbon tetrachloride is going to be something like 1 plus 2 divided by 5, that is 3 plus something like I think almost 13 or so, 12.5 or something, in which case it becomes something like 1.13 or 1.12. That means more complex molecules has a lower value of gamma, and therefore, now I tell myself if gamma is to be small, then the gases which are passing through the nozzle should be then the gases through the nozzle should be more complex, right. Gamma requires to be small, the gases must be more complex, but for Cp to be small, the gases must be simple. It is just opposite of what we want. Similarly, if we want the atomic mass to be small, well, we are also thinking of simple product gases. Therefore, we find that gamma requirement is somewhat contrary to the requirements of Cp and also molecular mass. Therefore, there is a problem, but we also know based on what we have studied so far, namely nozzle theory and Vj, that gamma is not very sensitive, and therefore we will not give very much importance to gamma. Therefore, what is it I have done? We said yes, I have a handle on this, the Cp should be small. Well, gamma decreases as the complexity of the gas increases. Well, I cannot have the same trend coming out from Cp and this together, therefore I will give less weightage to this because Cp directly gets into temperature. Now what is it I am left with? I am left with heat release and to be able to determine the value of Tc. Therefore let us take a look at heat release Q in a chemical reaction. Last point which I am doing is from chemicals, let us say. Let us have a chemical, we will call it as maybe chemical C1. This chemical gets converted to a gas like a product, let us say P1. We are just looking, maybe this chemical by itself reacts within itself and gives P1, or else I have maybe C1 plus C2 reacts to give me P1, product 1 and product 2. Now the question is, how do I get the heat released in these reactions? These are all chemical reaction of a component of a chemical giving two products, or chemical reaction between two chemicals which give me some products. And to be able to do that, how do we say when will I get energy from a reaction, from a chemical reaction? All of us have studied this both in combustion course and in the course on explosions. And how do we say any substance, any chemical will have its own internal energy? I call it as chemical internal energy of the substance. Now if it gets converted to product, and it will also have some energy like internal chemical energy of the products, instead of here I also use the same notation, internal chemical energy of the chemical as it is. The chemical gets converted to products. If you have more energy here of the chemical compared to products which have less energy, the deficit of energy is what we have as heat of a reaction. What is it I am telling? Suppose I have some chemicals over here, chemicals have some energy, this duster has some energy. Where does the energy come? Well, I have all these bonds together, it has some energy over here. Now I burn it and I get carbon dioxide, carbon monoxide, whatever I get. If the energy which is available here is more than the energy of the final thing, well, where does the energy cannot get destroyed? It manifests itself as heat, and that is the heat of a reaction. Therefore basically I need to find out what this internal chemical energy, or what is the energy available with the chemical as it were, which I call as internal chemical energy. You know, the word given to be able to describe this internal chemical energy is what all of you know very well, is what we call as heat of formation. And how is it defined? The heat of formation is the heat required to form a substance, any substance at standard state from its elements again at standard state. Let us put it down together. You know, we need to be able to describe what is the energy available in a given chemical, and to be able to find this we need some domain, some standards. We say, well, I say at a standard condition what is the energy available with the chemical, and how do I define, this substance could be, let us say, hydrogen, carbon, nitrogen, some substance like HA, Cb, Nb is this solid substance over here. What are the elements which constitute this? They are again hydrogen, carbon as a solid, again nitrogen as a gas, and mind you, these are all substances. Hydrogen is a gas under standard conditions, carbon is a solid under standard conditions, nitrogen is again a solid at standard conditions, I am sorry, nitrogen is a gas under and the standard condition is taken as 25 degrees centigrade, and 1 atmosphere pressure. In other words, if I want to form a substance at the standard condition from its elements again at the same standard condition, the energy what is required to form the substance is known as heat of formation. The notation is, well, I have to give some heat which is enthalpy, I have to give some more heat over the elements, that is an increment in heating, I need to form the substance, I will form it at the standard condition, therefore delta H superscript of 0 F is defined as heat of formation of any substance, any chemical, any heat of formation of a substance. If we know the heat of formation of a substance, then all what we know is, well, the heat of formation which is the internal chemical energy of the substance C1 which is the chemical is known, of the product heat of formation is known, and if there is a minus, that means if the heat of formation decreases I get energy, the heat of reaction is exothermic, I get some heat from the chemical reaction. This is all about the finding out the heat of a reaction. Let us put it together. Let us say I have, now I slightly expand myself, say I have a fuel F, I have an oxygen O, this gives me products. Fuel could be any fuel, maybe I take wood as a fuel, oxygen as oxygen itself from the air as oxidizer, and I get something like maybe some products like CO2, maybe CO, maybe something, some more of these substances. Therefore, now I say, well, my chemical reaction is fuel plus oxygen gives me, let us say, CO2 plus CO. I am not bothered, I just say maybe this is contains hydrogen also, therefore maybe H2O also. Composition of the fuel is known. Let us say I take A moles of the fuel, A1 moles of the fuel, I take A2 moles of oxidizer, and then I get B1 moles of one product, I get B2 of second, I get B3 of the third. Therefore, what is the energy released in this particular reaction? I tell myself there should be a decrease, that means the heat of formation of the products is B1 into heat of formation of CO2. Mind you, heat of formation is the heat required to form 1 mole, heat required to form 1 mole of the substance at standard condition from its elements again at standard condition. Therefore, heat of formation unit is joule per mole, and this is the mole, this is the joule over here. Therefore, plus B2 into delta HF of CO plus B3 delta HF of H2O. This is the value of the total heat of formation of the products over here. What is the heat of formation of the reactants? It is equal to over here A1 into heat required to form fuel, let us say oxygen fuel F plus A2 moles of this into heat of formation. Mind you, I should have put this standard all over here, all at the standard conditions, into oxygen over here. And now I say the change is like this, but only if there is a decrease I get this. Therefore, the heat energy which is given is equal to minus of the heat of formation of the products divided by the heat of formation of the reactant. This is the heat which comes out of a chemical reaction. Is it all right? You know, you all would have studied this in your combustion course, but anyway we need to go through this, because what is it I am trying to look at? I am trying to see what are those chemicals which will give me maximum Q. Therefore, that is why I am trying to again ask myself these questions. Are there some particular properties of these chemicals which make Q to be larger, and therefore can I use it favorably compared to the other cases. Let us take an example. Let us say I form carbon dioxide, I do an experiment, I burn carbon at standard state, maybe I take carbon which is a solid at 1 atmosphere pressure and initial temperature of 25 degrees centigrade. I react it with oxygen which is a gas, and now this is again at 25 degrees centigrade and 1 atmosphere pressure, and now I say I form carbon dioxide, again I want to form it at 25 degrees centigrade and at 1 atmosphere pressure. Then I say the energy required to form carbon dioxide from its elements Cs and O2 will give me the heat of formation, right. But all of you know, if I take carbon and burn, it gives out some amount of energy, large amount of energy, and the energy which I get from burning 1 kilogram of carbon is something like let us see, yes, is 32,800, I think should be joules, no, kilojoules per kilogram of carbon burnt. That means when I burn carbon with oxygen, per kilogram of carbon which I burn, I get something like 32,800 kilojoules of energy. Now what is going to happen? This 32,800 kilojoules of energy is not going to form carbon at 25 degrees, rather the temperature of carbon will go up. Therefore, if my product's carbon dioxide has to be at 25 degrees centigrade, what is it I have to do? I have to remove some heat from this reaction. That means I have to now remove minus 32,800 kilojoules per kilogram of carbon burnt, so that the products can again be at 25 degrees centigrade, right. Now therefore, the heat of formation of this should have something like a minus. When the reaction is exothermic, the heat of formation of, let us say, at standard state carbon dioxide should be something like minus 32,800 kilojoules per kilogram of carbon burnt. But this unit is something wrong, right. We cannot have kilogram of carbon here, and when I am looking at this, therefore better to refer it to something like kilojoules per mole of carbon dioxide. Therefore let's try to remedy the situation. What I say is, maybe per mole of carbon the energy which is released is equal to 1 mole of carbon has a mass of 12 grams, and therefore the heat release is equal to 32,800 into 0.012 kilogram, which is something like 397 . And what is it I have to do? I have to remove the heat, and therefore I say that the heat of formation at standard state of CO2 is equal to something like minus 397 kilojoule per mole of carbon, or per mole of carbon dioxide, because 1 mole of carbon gives me 1 mole of carbon dioxide. Therefore, per mole of carbon dioxide the heat of formation of carbon dioxide is minus 397 kilojoule per mole, and this is how we calculate the heat of formation. You know, any reaction which is exothermic will result in the products which have a negative value of the heat of formation. Let us take 1 or 2 small examples, because this is something which is basic. We will just spend another 2 minutes with 2 or 3 more reactions. Let us take the reaction of carbon as a solid at element level with half oxygen forming carbon monoxide. Now what is going to happen? Well, I have carbon monoxide here, I have carbon dioxide here, it is not fully oxidized. The heat which I get over here is something like 9208 kilojoules per kilogram of carbon burned. Therefore, now I can quickly do it. Therefore, per mole of CO formed, to form 1 mole of CO I need to burn 0.012 kilograms of carbon. Therefore, I get 9208 into 0.012 so much kilojoules per mole of carbon monoxide, and this is equal to something like 110.5 kilojoule per mole. And what is happening is heat is getting generated, carbon monoxide gets heated, I have to bring it back to the same standard condition of 25 degrees of oxygen element, of 25 degrees of carbon element, and therefore, heat of formation of carbon monoxide we say is minus 110.5 kilojoule per mole. This is how for hydrogen and oxygen to form water. Well, we have hydrogen plus half oxygen giving you H2O. Why I take this example is hydrogen is an element gas at 25 degrees, oxygen is a gas at 25 degrees, but water should be a liquid at 25 degrees, same standard condition. Therefore, now I can say that the heat of formation of water as a liquid at standard condition should be equal to the negative of the heat release per mole of hydrogen, which I think is something like 286, that is plus 286 kilojoule per mole of hydrogen. Now I am putting in terms of mole, and therefore, heat of formation of water as a liquid is equal to minus 286 kilojoule per mole, because 1 mole of hydrogen forms 1 mole of water. Therefore, this is how we determine the heat of formation of the different substance. Please let us not forget that since the heat of formation of a substance is defined with respect to the elements, the heat of formation of the elements themselves are therefore 0 at the standard state. One last substance I should take, because that has a positive heat of formation, and that is again important. Let us take the formation of hydrogen as an atom. We have H2 forming, dissociating to 2H. What do we do in this case? We have to supply heat to be able to form hydrogen atoms, and the amount of heat required to dissociate 1 mole of hydrogen is something like I have the value something like let us see, minus 435 kilojoules per mole of hydrogen, and therefore, that means the reaction I have to supply heat, that means the reaction is endothermic. Therefore, heat of formation of H is therefore equal to minus 435. I form 2 moles of hydrogen for each mole of hydrogen. Therefore, 2 moles of hydrogen atom per mole of hydrogen molecule, and therefore, the value is minus 117 to 217.5 kilojoule per mole, and this is plus, I am sorry, because what is happening is it is endothermic, I have to supply heat to element hydrogen, and therefore, it is plus 217.5 kilojoules per mole. Therefore, this is how heat of formation of the different substances are done, but basically one need not even do an experiment. If I have all the, let us say, hydrocarbon, I have the bonds which are known, I know the energy of each of the bonds, then I know the energy of the basic elements, I subtract the bond energy of the product or the substance from that of this element, I will get the value of delta heat of formation. But there are some subtle problems which come in. A product or a substance does not only have energy of the bonds, it could have some resonance mode also, it could act, it could exist in different forms, and therefore, it could have resonance energy. Therefore, it is necessary to have bond energy plus resonance energy of the substance minus the bond energy of the elements, which will give me this. This is a way of theoretically calculating. I think one should look at a book by Penner Chemical Problems in Jet Propulsion, wherein he gives a good treatment of heat of formation. The name of the book is, it's a beautiful book, Chemical Problems in Jet Propulsion. By S.S. Penner. If we now know about heat of formation, maybe now we can make some recommendations. Let us see what are the recommendations. I will quickly go through heat of formation of some of the substances over here. Well, we have fuel, and why not I put it on the board first. You know, when I have hydrocarbon, we say, well, a hydrocarbon could be saturated, it could be unsaturated, it could be aliphatic, it could be aromatic. What do we mean by all this? All what we mean is, if the carbon atoms in the hydrocarbon are fully saturated, that means all are single bonds, we say it is an aliphatic substance. If you say aromatic, well, you have something like a chain, a benzene chain, something like C, C, C and C, maybe a series of double bonds coming over here. These substances which have this typical benzene structure are known as aromatic. These are known as straightforward hydrocarbon or saturated hydrocarbon. Now, if we want to take a look at hydrocarbon, well, the simplest hydrocarbon is methane. The next one is ethane, that is CH4, C2, H6, maybe next is propane, next is C3H8, all are H over here, next is butane, C4H10, and so on the chain goes. Maybe by the time it comes to kerosene, it is little more longer in chain. Kerosene is dodecane, that is C12H26, and if you have lubricating oil, it is still higher, and so on the saturated hydrocarbons goes. Now, if I do an experiment to determine the heat of formation of these things, I find that the value of the heat of formation of, let us say, methane is something like minus 74.9 kilojoule per mole, ethane is minus 84.7, propane, which is C3H8, is minus 103.9, butane minus 124, and it keeps on increasing to kerosene, which is minus 292, which means a fuel, as it becomes more and more complicated or more and more longer in chain, has a higher value, higher negative value of heat of formation. If I go to a polymer, what is a polymer? It consists of a chain of carbon and hydrogen. Well, the heat of formation is something like minus 60 kilojoule per mole, but it does not come in this particular family of maybe the saturated hydrocarbons. It consists of unsaturated bonds, double bonds. We will be dealing with it when we get into something like solid propellants, when we consider solid propellants, as it were. Okay. Therefore, let's now tell ourselves, well, we find that for simple substances the heat of formation is smaller and negative, that is, for smaller or simpler substances the value of heat of formation is negative and small. As the substance becomes more and more complex, the value of delta HF becomes negative but larger. That means, can I write it as large negative values? This is just based on methane, ethane, propane and all that up to kerosene and all that. If we take a substance like hydrogen, which is again shown here, hydrogen is an element and therefore at the standard condition it is 0, because we are defining heat of formation, the increment of energy from the elements to the substance. Therefore, it has to be 0 for all the elements, standard elements, it has to be 0. Well, there are certain substances which are known as explosives, and explosives are substances which have inbuilt oxygen in it. That means it contains both fuel and oxygen within it. In other words, compared to a fuel, whenever I have a fuel, I react it with an oxidizer, it gives me products. That means what does the fuel do? It goes, searches out for oxygen and then it burns. An explosive is a substance which contains fuel plus oxygen. Such substances are known as explosives. As typical cases, instead of considering hydrogen and oxygen, if it could be integrated together, we could have a substance like H2O2, hydrogen peroxide. You have oxygen, you have hydrogen, and it consists of more oxygen than what is required to form water, and therefore this becomes an explosive. Similarly, you have substances like, let us say, nitrogen, N2 and hydrazine, and this again is an explosive because by itself it could react, or it could also have some amount of it could by itself react to form products. Therefore, such substances are explosives, and if we take some of these substances like let us say hydrogen peroxide has a heat of formation of minus 187.8. What is hydrazine? Hydrazine is what I wrote here, N2H4. It has a small positive value of heat of formation, something like plus 50. And if I were to consider some other explosive, like let us say I consider nitroglycerine. What is nitroglycerine? Nitroglycerine is something like glycerine, and glycerine is something like propane triol, and propane triol means I am looking at C3H5OH3, in which I replace OH by something like NO2, ONO2, it gives me nitroglycerine, and this again gives a heat of formation which is something like which is given as minus 370. Therefore, we are looking at the heat of formation of the different substances, and based on this heat of formation of the different substances, we would like to find out which chemical when it reacts gives maximum heat, and therefore under what conditions can I have chemicals which will give me a high value of temperature. I will continue with this in the next class. What I will do is I will go through the heat of formation of some more substances and find out what are the chemicals which are most viable for rockets, and we will zero down the number of chemicals which can use for rockets to something like 7 or 8 of them, so that we are very clear what to do for chemical propellants, right. Well, thank you then. I think I stop here.